So that's what we see here. This one you have seen only a slightly beautiful picture of the two-layer FSS reflector. The same, its performance. And how we measured it. Yeah, you have seen this. So how do you call this ultra-wide band? We look at the range within which the reflection phase is between plus or minus 90 degrees. Plus or minus 90 degrees, so this range. So that is basically from here to here. And that is the bandwidth of the reflector, ultra-wide band reflector. And this is another one that we published, the different design, its measurements with the ultra-wide band antenna. That's the one, a slightly different one we published in ICHIA, and this one is this, you saw this already. This is at 3 gigahertz, this is at 6 gigahertz. So at 6 gigahertz, there's some pattern is not very clean. This is the nature of ultra-wideband antennas at very high frequencies. It's not just one simple beam, but the back lobe, there's no back lobe. This is 3 gigahertz, this is 6 gigahertz, this is 10 gigahertz. Back radiation is reflected by the reflector. Measured gain versus frequency. Okay, DR antennas, I think we covered this already in the first lecture. We will get to EBG, electromagnetic band gap, later. Let me finish the FSS part first. These are some other meta material things we have done, but for guided waves, more like RF circuits, filters, etc., using Archimedean spiral metamaterial elements. Now this is FSS. This work we have done with University of Lund in Sweden and Pilkington Glass Company. This is related to energy saving glass, basically tinted glass. I think you can see those things everywhere in India and a lot of other countries. These are USA, Intel headquarters in USA, and few other places. Very common energy saving glass. It's called energy saving glass because it blocks heat waves coming into your building. So it can save air conditioning cost and air conditioning energy consumption. But how do they do it? They do it by putting several layers of metal oxide inside the glass, layer by layer, to block these heat waves. It's 1200 to 1600 nanometer infrared. But this comes with the problem. The problem is this coating stops good part of heat waves and a little bit of visible light. Right, we already know that when you look through this glass, it's not transparent as normal glass, but it's good. It's good for the eye. So they are both good. but it also significantly weakens mobile phone signals coming through it, and that's bad. And in fact, the 5G signals are really bad, this millimeter wave 5G signals. But this was well before millimeter wave. This was just simple RF mobile broadband. So they attenuate Wi-Fi signals. That is good. So your Wi-Fi will not go too far outside your glass room. But mobile phone is a problem. Mobile transmission through this glass. So my PhD student Gaffer Kani went to Sweden. This is a professor in Lund University. He's an expert in this area, and they did these measurements using, this is in Sweden, Lund University lab, transmission with a very wide band antenna measuring transmission through glass, different types of glass, to characterize this loss. And this is what we want to do. Heat is reflected, or whatever, heat does not get into your building. And Wi-Fi in the building will not go out because of these layers. Visible light, there's some attenuation that is good. This is the problem. Cell phone signals are attenuated and weak inside the building. So improving mobile phone signal transmission without significantly compromising other things. If you remove the energy saving layer, metal oxide, then you get signal. But you don't want to do that, then you get infrared heat and all that as well. And so this is ordinary gas. Normal gas lose about 49% of wanted heat in winter, and gain unwanted heat in the summer. Energy saving glass, that's the subject of this research. Metal oxides, tin and silver metal, that's coated internally on the side, provides high infrared attenuation, etc. There are two types of them. One is soft coating, other is hard coating. Soft coated one is easy to remove, can be damaged while handling, but it was easy for us to etch out, remove. Hard coating is quite hard to remove. We have worked with both types of glass. So if you just measure transmission through this glass, this is a transmission. This solid line is the transmission through glass with full coating. Okay. So we had to find a solution to get better transmission of some mobile signals, cell phone signals. So we're targeting this frequency band, and we etched an FSS in the metal coating. So 4 apertures represent the truncated frequency electric surface. It's only 4 elements, not a very large FSS. This is the unit cell. So design the unit cell to get good transmission around these frequencies. And we got a excellent improvement, like 15 dB improvement in transmission by just few slots. We only removing, we don't remove metal, we only remove the metal oxide, the lossy layer. Don't remove the glass. But because we remove that, it will increase infrared transmission by about 10%, because infrared can go through this FSS slit. But it increased signal transmission not by 10%, by 15 dB. And this is how this was made. This is a paper in nitrile transactions. So a lot of details in this of what I presented today. They are in papers. And this is the machine in Lund University that fabricated this. And this is another one. I think this was done on the hard. We tried both soft coated and hard coated circular patterns etched out. 9% of coating is removed to improve transmission over a quite large band. You can see this is from 0 to 2 gigahertz. You can design, it's like a filter, increase in the transmission. And it was created using laser micro machining again. The transmission varies in this band between 0 dB and minus 11 dB. Transmission bandwidth of 1.5 gigahertz. So you can get most of your cell phone signals through the glass by this